Is the screen visible?
Yes, sir.
Good. So we were in the process of discussing about the generalization in learning, and if you remember, the generalization means, see, we are given with only the training examples. We do not know the unknown function, and therefore the traditional learning that we need to do over the unknown function, that when we only see the training examples and try to learn something, how well we generalize in with respect to the unknown situation. That's what the concept of generalization. And we tried to give it a theoretical flavor, meaning that we tried to sense this factor that we will learn in such a way that our out of sample error, that is what we cannot foresee, if we give a hypothesis and we test over the unknown unforeseeable space, we should have a good approximation by that hypothesis. So that hypothesis should be good. In order to do so, we followed two paths to converge into this generalization. So this is what the generalization is, the meaning of generalization is all about, that whatever you learn, generalize well out of sample, providing the out of sample error almost zero. And when we did that, we do it in two steps. One, we tried to minimize whatever we can see in sample, that is minimize the error with respect to the training point that is given to us. Plus, we also try to see that how well we the and we also try to see that how well we foresee the approximated hypothesis, how well it actually approximates the out of sample conditions, by saying that if there are low error here, then there will be also low error in the out of sample region as well. So together with these two factors taking together, we get E out equal to 0 in a kind of a different two conditional way. And if you remember that this is the thing that we did throughout the previous week, which is our all learning algorithms that we studied. That our learning algorithm tries to minimize what is E in and try to make it almost close to 0. That is minimize the in sample error. That is what the learning algorithm does. In terms of this is actually what we called as the feasibility of learning, and started to give a boundary of this, that how well the in sample error tracks my out of sample error. And in terms of feasibility, we started off with something called as a web Hobding inequality, which says that the probability of some bad events happening, that is my E in is not tracking. So all of these are with respect to the hypothesis that I gave, is not tracking my out of sample, and it gives a drastically big error. This should be bounded by some probability value, which should be small, but Hobding inequality suffers from a drawback, that it has a very large factor m into picture, which is the primary hindrance in generalization, because this is the size of the hypothesis set, and it could potentially be infinite as well. We have seen in a simple model like perceptron, the hypothesis sets is infinite because I could choose any weight in the continuous domain and could make separate different hypotheses. So the quest that which quantity may replace this m brings us towards the notion of something which we call as a growth function. In the last week, we started off with that with respect to a given hypothesis set, our growth function is a function that I will give you n. You are supposed to place the n in such a order that it gives you the maximum number of dichotomies. So this is the maximum number of dichotomies realized by n function over our approximated hypothesis set, that is H. So in case of perceptron, we have seen that up to 3 we could generate all possible dichotomies, that is the levelings in all possible ways so that the linear separator can separate. From 4, we did not get such a thing. So what we found out is that there is something which is called as a breakpoint, meaning that, so we also introduced, so in terms of having this as a growth function, so this is the notion of growth function we started off. But computation of growth function is indeed very difficult because for every n it's a number, so it's a function and you need to compute for every n to see it. Rather, we thought about something called as a breakpoint, which is basically a value k where I will find that this is actually less than 2 to the power k. So therefore, we can say that for all value I which are less than k, my growth function on those I is equal to 2 to the power I. Right? This is quite easily understandable and we got a concept of the breakpoint. And then what does it suggest? The concept of breakpoint give us is that this is a very particular observation that we made, that if k is finite, that is if the breakpoint k is finite, this will imply that mh of n is a polynomial. And we prove this factor by having this recurrent kind of a mathematical induction kind of a behavior, where if you remember, this proof was made by small lemmas where we try to prove, suppose this is the maximum number of dichotomies possible with n points having a breakpoint k, then we prove that this is equal to b of n minus 1 k plus b of n minus 1 k minus 1, and which gives us that the number of dichotomies in a maximum possible, which is also this quantity, is upper bounded by this equation I equal to 0 to k minus 1 nci, this equation. And indeed, we have seen that this equation is nothing but it's a term where the maximum, the highest term is to the n to the power k minus 1, and obviously it's a polynomial because my k is a constant and it's a finite breakpoint and hence it's a constant. So this is a polynomial quantity, and we can suitably claim that if this is finite, then we got a growth function which is polynomial. And we ended up with the lecture with the second part of this proof, that yet we have not reached this position, that what could replace this one. So the second part of the proof that we left in the last weeks by saying that can this mhn be a good function to replace m? So this question we ended up in the last lecture and stopped there. Actually, this, to make the infinite dimension probability boundary to a finite notion, is the most important contributions in machine learning, and which is obviously called as Vapnik-Chervonenkis bound, which is, in short, we call it as a VC bound. It is so novel contribution that it itself is a paper. So what we will try to do, so that you do not get bogged down into epsilons and deltas, I will not go into this proof because it's a full paper proof. I will give you intuition that what potentially it means, that a polynomial function could reduce the bound from the infinite space to a finite space. And I will use some pictorial description so that you get into this factor. Then later when you read the paper, which is obviously not in the scope of this syllabus, when you read the paper, if you wish, you can easily understand with those conceptual notions. So let us proceed with the fact that what happens why the Hobding inequality is a failure for the generalization of union boundaries, that we say that any hypothesis if I take can get a bad event can occur, and it could be disjoint, and therefore we need a union. So we can think it of as a particular space. Let's say this is my first space where this is a space of data points. Data points meaning that any particular point here is actually a data set. A particular point here is actually a full data set. A full data set means that is x1 up to xn, the n training examples. Now, what does Hobding inequality does? So let's say this is my what does this Hobding inequality do? Hobding inequality tries to find out the bad region and try to bound it. Therefore, you could see there are certain things that here maybe this is a bad region. I just color it like that. Bad points where my hypothesis doesn't perform well and I bounded it here. But when from this point I went up to the union bound, then what happens follows that suppose I went up to the union bound, then assuming that anything could happen in a disjoint space, I get on coloring the bad events one by one, and that in turn eats up my full space, and I get such kind of a weird bound which is undesirable and which is not practical because these hypotheses are not disjoint at all. Right? That's what the union bound says, that bad events can occur anywhere, and wherever the bad events occur, I just have to union it to be very pessimistic way that it could be disjoint, and hence my probability boundary could be an union of all those. So it may so happen, and now see the thing happens when it is infinite. In infinite means it just fills this whole data point set as everything is a bad for some hypothesis or all. So that's the question of there is a possibility that this point could be a bad, yes, because there is an infinite hypothesis space. And this restricts us to the capital M, which is potentially very bad in terms of generalization bound. Now the intuition. The intuition behind what does MHN brings in. Just try to think in this manner. You are given a space, as we are saying a dichotomy or something, you are given a space where you do not know what the final classification function would be. You do not know that. Rather, you are given with certain points in that space as your training example, and you only look through the color of this point. Hence, what happened, this hypothesis and this hypothesis and this hypothesis, all of them, the infinite spaces of moving a hypothesis into this region without changing the color of the point, all become treated as equivalent, which means that the same space, if yeah, any question? Which means the same space, now what happens that suppose I have a bad region like this, a shift in the hypothesis makes equal contribution with a slightly beyond the overlapping region. Another hypothesis makes a equal contribution with a slightly overlapping bad region. Another hypothesis makes a equal contribution of bad with a slightly overlapping from that. Due to this nature, you are only seeing the dichotomies. That means the change of a level of point is now dictation of your newer hypothesis set. And you are trying to see how much generalized I can do in terms of the hypothesis. And that's why you are trying to find a number which can settle. And 1 plus that number is a breakpoint. So this is the overall understanding why this whole union bound is just a very pessimistic assumption rather than thinking in this way. But still, I mean, to get you another analogy, so what this MHN function does, MHN function guarantees you that a particular data point, let's say, will be colored m number of times. For example, if if I have a guarantee on that a particular data point will be colored m number of times, which means here in case of Hobding inequality and the union bound, I do not have this guarantee that every point will be colored m number of times by m number of hypotheses. If I have this guarantee, you can say the bad event space will be shrunk down to the total space or the total number of points by m at least. Because if I can say such kind of a guarantee that a point could be colored m number of times by different colors, therefore the number of points colored in the total space will be the number of points that has been colored earlier using union bound divided by m. That's a straightforward algebra. This is the motivating fact that why we can find out in the VC bound the space of bad events to be very congested, not spanning the entire space. That is point number one, or the intuition number one. The second intuition, if you now look into the formula, what we want, this was the formula that we wanted, right? We want to bound this formula with something. Now here the culprit is this one, because when you go to the number of dichotomies, you do not know what is out of sample. You only know the number of dichotomies with respect to n points. That is, only n points you look through the holes. Nothing else is in your hand. Therefore, we need to do something about this E out, right? Because this otherwise, if I can only see what is in sample and need to predict this bound, this particular quantity I need to get rid of. Otherwise, how can I say that only looking at my points I can generalize over out of sample? For that, the statistical thing comes into picture, and again we can go with our bin analogy. Remember the bin analogy that we have in the bin, certain number of points we have where I can color it as a blue or as a green or red, depending on the hypothesis that you pick up is a correct or wrong. If you remember it, that is E out of G, and a sample from this particular set, if I collect, that sample could look like this. That is a sample of n points that I have. Okay, and then with respect to this sample, I dictate my E in G. Now, in order to get rid of this particular function, what we do is as follows. And I mean, what Vapnik-Charbonenki's thought of is as follows. That let us try to see this analogy of the same bin, not only with one sample, but possibly drawing two different samples. So what does it signifies by drawing two different samples? Suppose you are doing a presidential poll election where you are trying to find out by seeing the whoever they have trying to elect, that voting exit poll, you are trying to predict that who will win. Now, it is very likely that if you have a sufficiently large sample, then two different sampling could lead to same answer of whoever wins, right? So that is the probability value that comes in, where I only give one particular hypothesis of winning, but I have two different samples to look for to it. That means instead of trying to say that E in will track E out, which we need here, we modified this problem to say that E in will track E in dash. with respect to that particular hypothesis. That's what the change we make here. You might argue that this may also lead to something not impossible, as we see for the feasibility case, that there may be a scenario if you go on keep on repeating this two number of points multiple number of times. If you keep on repeating it, there will be a scenario where this does not match. It horribly tracks each other. But that is the question again comes of the feasibility. I mean the possibility versus the probability. It is probably correct that two of this exit poll will match given there is a voting and somebody is a winner there. So which means that if you combine these two, what you get is that we can get rid of E out by having more number of samples than we have. Right? Earlier we started off with n samples and tried to figure out what is the bound. To get going with this analysis where two samples of different, I mean two drawn samples will track each other, we might need more number of samples. With these two intuitions, what happens exactly, the proof comes in this way. The outcome of the proof says that my E out G and E in G greater than epsilon, this is basically not 2m, that the m directly do not replace by mh. The formula is this, which they found out. Now see the point, this 2n because of this factor, that I need to now take more number of points into consideration so that I can track each other instead of going to the out of sample. Because I do not know out of sample, I have to pull off my opaque sheet to look into the function. I only look into this particular dimension with respect to the holes and their dichotomies. So what it did that we need more number of samples to bound it. However, it's a polynomial bound if you have a breakpoint k. This is a polynomial bound because mhn is a polynomial. So mh2n will also be a polynomial because it is of the order of 2 to the power k and to the power k minus 1, where you can understand 2 to the power k is constant because my k is a constant finite breakpoint. So this is what we call as Vapnik-Chervonenkis inequality or Vapnik-Chervonenkis bound. And this is one of the most significant result in learning, where they showed that whatever you learn in sample with respect to sufficient number of data points or training examples can equally be good to predict your out of sample error. So this is kind of a pictorial interpretation of the proof that I have given, but this is a Vapnik-Chervonenkis paper and it's a very popular paper, very well cited and very important paper in machine learning paradigm. So this concludes the fact that indeed learning is feasible from a generalization point of view as well. Okay. Good. Since now we look into the concept of Vapnik-Chervonenkis, so there is something called a VC dimension that we need to look into now. That the concept is very simple. I mean, maybe some books complicate it, but the concept is very simple. Since you know the breakpoint, so the VC dimension, we call it DVC with respect to a hypothesis set H, is nothing but breakpoint minus 1, which means that the largest n, this means it is the largest n that can get shattered by H. Yes or no? Right?
Yes, sir.
Therefore, two important considerations here. I mean, you can easily follow if I write it. All n is less than equal to dvc of h, then we can say h can shatter n points. Why this is the case? You can see k is a breakpoint, so any point less than k, all of those points, the values of those n's which are less than k can be shattered. That's what the first condition is. And the second condition says that if k is greater than dvch, then obviously k is a breakpoint for h. Now you might argue that why, if there is a notion of breakpoint, what does it help to another? To introduce another such kind of a thing. Actually, the proof of BC dimension, I mean, it comes from a different angle rather than from the breakpoint angle, where they try to say that my MHN, earlier we saw that it is bounded by I equal to 0 into k minus 1 NCI, which is nothing but, you can see now k minus 1 is DVC. It looks nice, right? I mean, instead of k minus 1, it looks nicer that I have this function as represented with DVC, which means I can say this function is polynomial with respect to VC dimension. That's what the maximum power is DVC of n. And with that, you can easily take certain examples to refresh your thoughts about breakpoints and VC dimensions. And I assure you, this is the last time we are seeing this positive rays and all. So just tell me, what is the, in case of positive rays, what is DVC and what is K? Tell me, what, in case of positive rays, what is DVC and what is K?
N plus 1 in positive ray.
No, why? Positive rays in a line, a point beyond which everything is plus 1, below which everything is minus 1. How can you shatter n points there? You can shatter only one point, because 2 points if I gave, you cannot make these 2 points such that the left is plus 1 and the right is minus 1, right? Left is plus 1, right is minus 1. You cannot do it. Yes or no? Because I will give you an A beyond which the right side is plus 1 and the left side is minus 1. So how can I shatter 2 points? Are you getting it? Yes or no?
By only for one.
Yeah, so DVC is 1. This is 2. Breakpoint is 2. We established that in the last class, isn't it? Positive
Yes, sir.
interval. Positive interval. What do we
DVC
establish?
2.
This is 3. This is 2. 2D perceptrons. What we established? This is 4 we established, right? Because 4 points, you forgot everything looks like. 4 points I cannot shatter, right? Every combination, I cannot shatter this. These two are one level and these two are different level. Can I shatter this with a linear line? Can I make everything? No. This combinations and the vice versa, we cannot do it. So we have found out that MH of 4 equal to 14. Remember? So breakpoint
Yes,
is
sir.
4. DVC is 3. The VC dimension is 3. And the final examples that we earlier gave was the convex set. So here you can see, because as you can understand that if I place in this way, any order I can make my plus 1 points and minus 1 points. I can take any of them in this in if I put it in terms of a circle, isn't it? Yes or no? So therefore,
Yes,
we
sir.
saw that the breakpoint is infinite. There is no breakpoint. I can shatter anything, any endpoints. So the VC dimension is infinite, right? So therefore, you can see this VC dimension depends on, if you try to remember the learning diagram. Now VC dimension depends on, I want to get a G which will approximate my F, and the VC dimension is with respect to the fact that G generalizes well. So VC dimension obviously depends on the final hypothesis. It is independent of the learning algorithm because I do not want to know any learning algorithm. See, positive rays is a problem where I get this VC dimension. This is another problem where I get this. I do not know how I am learning it. I only know what will be my separator. It's a linear, and therefore I could not shatter all points up from n equal to 4. So it's independent about input distribution. It is independent about the learning algorithm. It is independent about the target function that you are getting in, because anyway you do not know that. It's only dependent, as you know, with the hypothesis set, because it's a perceptron. It's a positive interval, that is the hypothesis set or the power of hypothesis set that you want to make, and it's dependent on the final hypothesis that you are trying to produce here. Okay. So these two concepts are clear, right? I hope breakpoint and VC dimension.
Yes, sir.
Now, an interesting thing I would like to make you look at 2D perceptrons. We can say that the VC dimension is 3 for 2D perceptrons. I will just try to prove in front of you one thing, that for 2D perceptron in D dimensions, the VC dimension will be D plus 1. So in other way, I will try to prove that a set of n equal to D plus 1 points in the D-dimensional space can be shattered by perceptrons. So let me start proving it. I have to prove, you can easily understand, to do this I have to, if I prove it that DVC of perceptron hypothesis is greater than equal to D plus 1, and if I can prove DVC of perceptron H is less than equal to D plus 1, then I am done. Right? If I can prove these two, this two implies the fact it should be equal to D plus 1. That means n equal to D plus 1 point can be shattered only, not more than that, beyond which it's a breakpoint. Right? So this will give me that DVC of H is equal to D plus 1. That is what I want to prove. Now let me give one side of the proof. I will not tell you which one I am doing. Either I am doing one or two. You guess and try to tell me at the end of one part that which I have proven. Let us say that I have n points. As you can know that n points in D dimension, which means it's a square matrix of D plus, so rather I have n equal to D plus 1 point. So I have D plus 1 point. It's a square matrix of D plus 1 cross D plus 1, because each point x1 transpose, if I write, it starts off with a mandatory 1, that is your x0 value. Remember in perceptron, and the rest is your D numbers, right? So each of them, and we have D plus 1 points. Suppose this is my input matrix or the input set of points I have given it. Now I will take these points in most generic way possible, that the first point everyone is 0. That means it is, just try to think about 3 dimension, it is this point I am taking. Isn't it? Everyone is 0 means 0, 0, 0, your x coordinate, your y coordinate and z coordinate all are 0 means this point. Then I will take x equal to 1, the other ones all are 0, which means I am taking this point. Then I will take y equal to 1 and the other ones are 0, which means I am taking this point. Then I will take z equal to 1 and the other ones are 0, which means this point. So This is the most generic setting I can make of all my d plus 1 points. Yes or no?
Yes, sir.
Right? The important point to look here, the fact that I will use in my proof is that this matrix X is invertible. Why? Because first of all, X is a square matrix and X has determinant as 1. It is invertible because X is a square matrix. It is invertible because determinant of X is 1, because 1 into this is 1, rest are 0. So you can see the determinant is 1. So X is invertible. That is our first thing that we noticed. Now, the thing is that can we shatter this set of d plus 1 points? If I can say I can shatter this set of d plus 1 point, then either one of them has been established. Either this or this, you tell me which one. So my first go is that can I shatter these d plus 1 points? That means for any y, I choose which is y1 up to y d plus 1. Any y, that means it could be plus minus 1, it could be plus minus 1, up to any one could be plus minus 1. Can you find a vector w satisfying sine of xw equal to y? Then I can say that all these points are shattered, because any arbitrary choice of y, if I can find a w that can produce that y, then all of these points can be labeled arbitrarily. All possible dichotomies are possible, so it can be shattered. Yes or no? It's a perceptron.
Yes, sir.
So this is pretty easy, because instead of taking the sign to be satisfied, I just make this, because I have these points. So therefore my w will be x inverse y. Why I am taking this one? If I could make, instead of sign xw itself be equal to 1 or minus 1, then their sign will also match, isn't it? If xw itself is 1 or minus 1, then their sign will also match. It is easy because this is invertible. I am using this fact, and the y, I know any combination of y I can get a w, right? Yes or
Yes,
no?
sir. Yes, sir. Right.
That means we can shatter d plus 1 points. So now my trivia is to you is that what does it prove? Does it prove that dvc equal to d plus 1? Does it prove dvc greater than d plus 1? Does it prove dvc less than equal to d plus 1? Or does it gives nothing, no conclusion? Multiple choice. Which one do you think? A, B, C, or D? What I have proven?
C. I
Any
think.
everybody C, or somebody anyone has any other concept? See, if you can shatter d plus 1 points, then I am saying that dvc is at least d plus 1, because any other point less than d plus 1 you can also shatter as per my vc dimension definition, isn't it? If we can shatter d plus 1 points, then d points we can shatter, d minus 1 points we can shatter, d minus 2 points we can shatter. So dvc is at least d plus 1 in that case, isn't it? Yes or no?
Yes, sir.
So we have proved this one. The dvc is at least d plus 1, right? For the sake of non-ambiguity, let me remove all this. So we proved this one. So therefore, we have proven this factor. How to prove this? Can you give me anything that how can we establish that it is exactly equal to d plus 1? What needs to be proven? What simple thing needs to be proven rather? We need to prove that d plus 2 is a breakpoint, isn't it? That seals our proof. If I can prove d plus 2 is a breakpoint, yes or no?
Yes, sir.
That means I need to prove that we cannot shutter d plus 2 number of points. Okay, next part of the proof. Here what we will try to see that let us take d plus 2 point. So d plus 2 point means it's a vector of d plus 1 dimension. Each of them is a vector of d plus 1 dimension, and I am taking d plus such 2 such points, right? And my claim is that I have to prove that not all possible combinations of this dichotomies can be possible with this d plus 2 points. One immediate observation, we now have more number of points than the number of dimensions. Yes or no? Agreed? More number of points than the number of dimensions allowed.
Yes.
Therefore, for a particular j, we must have a linear dependence with respect to all other d minus d plus 1 number of xi's. We can have a linear dependence for a particular j with other points. Agreed or not? See, it is just like telling that suppose I give you equations with x and y's, I give you 3 equations with x and y's. Definitely the third equation will be a linear combinations of other 2 equations. Any one equation would be such. Right?
Yes, sir.
So this is one factor that we will try to use. Second factor comes from here that not all AIs are 0. This is the second factor. Why? Because d plus 1, this each individual point at least have a 1 in the front. The rest could be anything in the point. But this is my x0 of the perceptron. So if all of xi is 0, then xj would produce an all zero vector. That is not possible. So some AI should be 1. I mean, should not be 0 rather. Agreed?
Yes, sir.
Yes, sir.
Good. If you agree till this point, now I will tell you that consider this dichotomy, whether I can realize it or not. So when I say I could not realize all dichotomies with d plus 1 point, I will give one counter example dichotomy. That will suffice to prove that all dichotomies are not realizable. So consider the following. Let's say xi's with non-zero AIs get yi equal to sine of AI. Xi's which are having non-zero AIs gets yi equal to sine of xi. This is a particular dichotomy, right? Those xi for which AIs are non-zero, I give the yi corresponding yi as the sine of this AI. One dichotomy I am trying to construct. And I assume that xj gets yj level yj equal to -1. This is one dichotomy I am assuming that can I construct this. Are you getting me where I am trying to reach? I am trying to show you that one such dichotomy, even if I wish to construct, I will be prevented. So that means all possible dichotomies are not realizable. Are you with me?
Yes, sir. Yes.
So therefore, when I say this kind of a dichotomy, it immediately points out from our this formula that xj equal to sum of ai xi, where I is not equal to j, which means wt xj is equal to sum of ai wt xi. Now see the point here. Look at this equation very carefully and try to realize this point. My dichotomy suggested my yi should be equal to sine of ai. Perceptron says the yi is equal to sine of wtxi. Therefore, sine of this and sine of this should match, which means this should be greater than 0. If these two signs match, this should be greater than 0. Yes or no?
Yes, sir.
This forces the sum to be greater than 0. This forces my yj, which is basically sine of wtxj, to be leading to a contradiction with respect to the dichotomy that I have assumed. Therefore, not all possible dichotomies I can realize with d plus 2 points. Conceptualization is clear to you what I want to make?
Yes.
Everybody? Anybody has any problem? So finally, we reach that an d-dimensional perceptron has a VC dimension, which is d plus 1. See, it's an enormous result because I can now say that I am bounded with my generalization boundary with the order of n to the power d to the power minus n, isn't it? Because my generalization boundary suggests me the order is this e to the power this minus n. So therefore, I can say that I am bounded in my generalization by this factor. Though I can take infinitely possible hypotheses. And this d is not large, as we see in 2D perceptron it is 4, and if in a d dimension it is d plus 1 only. And it should be the case because it's perceptrons are very simple model to get realized. So that's why it should be the case. It should not be very I would say generic. So that's why we get a less spacey dimension. Intuitively, what does it suggest? One thing is sure that if you look at this formula, what does DVC suggest? One thing is the fact that it suggests the degrees of freedom. First of all, you have an analog set of knobs or weights in the perceptrons, which you made it in terms of a binary kind of a d plus 1 notion. That's why we could reduce the generalization by a very succinct factor. So one thing is that your degrees of freedom, where it is infinite due to this analog nature of weights, you reduced it into a equivalent binary degrees of freedom, so-called binary, with just d plus 1 dimensions. The second thing is the fact that what indeed it suggests. See, there is a relation about how, I mean, what are your number of attributes or parameters that you wish to learn, and with your VC dimension. Here you see, this is 1. Here it is 2 because you can see that I want to learn a range from A to B. So the number of parameters have an impact on the VC dimension. Similarly, here you see that it is 3, or rather in general case it is d plus 1. Now, if you try to consider the figure of perceptron, you will understand why it is d plus 1. You can see here this is x0, this is x1, this is xd, and it is dictating my perceptron output, which is obviously h of x. And you can see here there are d plus 1 parameters. So definitely VC dimension has a significance in terms of the freedom that we give to make a decision. That is the number of parameters in our hand. But it is not directly, as we see in these examples, it is directly related to exact number of parameters. It may not be the case because let's say cascade the set of perceptrons one after another as we do in neural networks, but we cascade the set of, instead of logistic unit, I cascade the set of perceptrons. You may easily argue that even if it's a single input with respect to the mandatory x0, you can easily see here the number of parameters is exponential. This is 2, here coming again 2, here again 2, because all of them parameters means the different weights. So this is also has some kind of a weight. Here also the x0 comes with some weight. So all of these parameters you can see that the number of parameters are exponential. However, the outcome that you will get does not vary when you get an outcome here. Because when you say something is +1 or -1 here, going through another round of summation and another round of up and down will only flip the level or do nothing else. Depending on this weight, it will just flip the level or do nothing else. So beyond the boundary of one perceptron, if you cascade it without without knowing anything, just like not a non-ML expert, then what will happen? It is not the number of parameters that matter to the degrees of freedom or the VC dimension. It's the number of effective parameters is actually proportional to what we call as the VC dimension. There are some intuitive observations from this perceptron or from the VC dimensions that we can get. Right?
Yes, sir.
Okay. If you get that, now let us see that where we will reach with respect to the formula that we have in our hand, and I will finish it off. Maybe 5 minutes, give me time, I may exceed, but I can finish it off with this last statement. Somebody has asked me maybe in the chat of MS Teams that why this term is not 2 in some books. This is the reason. I hope you got the reason now, because that Hopding inequality was not the actual bound. Okay, so now look at the fact that sometimes we call this as delta, or the confidence that we can bound it, generalize it. And you can see that this delta term is nothing but it's a order of, as I said, n to the power d, where d is the VC dimension, e to the power minus n. Now, what is with respect to DC dimension? If I know that the perceptron DC dimension is d plus 1, how many data points do I need to learn? It could also have a answer to that. So first we will look pictorially or graphically that how many data points will be is good to learn. There is no theoretical proof of this, but some kind of experimental results. So you see this term, if you try to figure out, so suppose your probability value here is 1, which is governed by the bound. Your boundary probability here is 1, rest of here is more than 1. Now, when your n is small, this is n, and this is your probability. When your n is small, so it, with respect to the d, it rises up, and then it shifts down. It comes down. So if you look at the nature of the curves of n to the power d to the power n, so n to the power d is kind of this. After certain points, e gets dominated, and then it will come down and finish like this. It looks like this. So if your d becomes much higher, if it is VC dimension is more, let's say n to the power 30 and all, then you will get a curve like more steeper, and then it diminishes like this. If n is more, then your curve will be more steeper, and it diminishes like this. Then e to the power x minus x takes over and it diminishes. But our range of importance is below this one, because more than one probability we do not care to learn in machine learning course. So what we will do, we will try to make this scale as a log scale and see what does this part to blow up. So if you blow up this part, what you will see here is that, let's say this is your 1. So effectively the orange curve that I have drawn, you will see now here this kind of a relation. Then the blue, the green curve that I have drawn, this kind of relation. the blue curve that I have drawn, sharp up and this kind of a relation. So what you will see that with the increment of DC and N, a rule of thumb is to take N to be more than equal to 10 of the DC dimension values, so that you can get as less as possible with this 1.0 probability line. And it just linearly, if this scale is log, then it linearly gets deviated with respect to the number of data that you need with respect to VC dimension. So this is a rule of thumb. So that is nothing theoretically established. This is a rule that you take the number of samples at least 10 times your VC dimensions to get a meaningful generalization. That is point number one that I want to make in terms of pictorial thing. The other thing is, looking at this, I can reconstruct the equation. See here, this is what? This is the probability of something bad is happening. So now how good I am generalizing? It is nothing but the probability of E out minus E in less than epsilon, which is basically 1 minus of probability of E out minus E in greater than epsilon. Obviously, you can see this formula. So if you take this one, this will give us that probability of actual function is not matching your hypothesis. This is very less, which is covered by this here. So with probability more than 1 minus delta, I can say that your function will match the actual hypothesis, the target functions that we have. And often this concept is known as probabilistic approximate, sorry, probably, not probabilistic, probably approximately correct, probably approximately correct learning, or in short we call it as a packed learning. And some of you may know that this has been invented by Leslie Valiant, which is a Turing awardee, due to only this concept where he has shown that learning is feasible, the pack bound. And since we have an equation of this kind of nature, we can already, you see in terms of delta and n, I can get the epsilon, because just to simplify this equation in many book, so just to blow up with this equation, we have 4 mh 2n e to the power minus 1 by 8 sigma square n is my delta. Now, with respect to this, what will be my epsilon? So you can take a log and commit here both sides, and then if you take the square to be a root, so 8 by n this side will come, and then ln 4 of whole this thing by delta. So this is root of 8 by n ln 4 mh 2n by delta. Sometimes you will see this is the error that generalization will make given delta and the number of points, which means we can say that we also can tell that this is, let us call it as a term omega, which is dependent on n, h and delta, and therefore E out and E in, this one is less than equal to omega. So why I am saying this? Because see, this is the generalization bound, right? This is the generalization bound, which pictorially means, as I drawn it in some day, that which pictorially means that your in sample error goes like this, or rather the other way. Your in sample error goes like this with respect to your learning. Your out of sample error goes like this after a certain point. And then you need to figure out a sweet spot, as I have told you, that is the dimension of VC. And in between the difference of that is the generalization bound. So obviously we write it simply as E out minus E in. There is a reason for it, less than equal to delta. Just remove the absolute values. The reason being that E in is purposefully the term that you want to minimize through your learning algorithm. E out you cannot see. So it is mostly the case that the E in is almost close to zero where you have certain E out. So this term is proper negation. So E out minus E in is proper rather than the other way. And I want to generalize it with respect to certain bound, which is called a generalization bound. So that is the gap that I would like to foresee in my learning, and I will try to reduce this gap or the probability there. So epsilon, remember epsilon is the error between E in and E out that I want to reduce. So obviously my E in plus epsilon is what my E out should be there. That's how I generalize. When I say my E in generalize the out of sample, I want to make sure that the E in plus this error will generalize my E out, right? This error. And that's what the generalization boundary is all about. Okay, till this point.
Yes, sir.
This is just a mathematical jugglery I have played here, nothing much, to show you that there is a notion of generalization. What you learn plus the error must match the E out. And what you learn plus the error, that error will get, you have to minimize this epsilon. And you can see that this formula says that your epsilon get minimized if your MHN is polynomial. You are very realm of minimizing it with a finite number or a polynomial number of h. And as we have said, it's called a pack learning because when your MHN is polynomial, that means, see then what happens if your MHN or the number of samples is reasonably low, which means that you could train it in polynomial time. This also implies that in poly time, I could train the model. If this is very much high, my hypothesis space is such generic that I can shatter all possible points, then polynomial training is not possible. That's why the notion of pack learning says that it is probably approximately correct with respect to polynomial time learning algorithms and the hypothesis sets. So that's how eventually it gives us an intuition about VC dimension and finishes the whole thing. So I would like to go back to the first slide. So we started off here and we just finished here with the VC dimension. So this is the overall generalization concept that we applied. Apart from the fact that when we generalize with VC bound, our VC bound delta comes as 4 growth function of 2 number of thing minus 1 by 8 error square n. So this is the delta function. With respect to delta epsilon, I give my E in minus E out, this generalization bound for bad events. So for the good events, it's just called a pack bound, where it also suggests from this MHN what Leslie Valiant showed, that there will be a polynomial time algorithm to train and learn something which is good enough. Okay, so if there are any quick questions, we can take. Otherwise, I'm sorry that I'm 5 minutes over.